Hello everyone, my name is Ned Dimitrov, and today I'll tell you about the Epidemic Disease Control System, or DICON. And this is joint work with Sebastian Gall and Lauren Myers at the University of Texas at Austin. And this work was funded by a supplement to a Midas grant with PIs Alison Galvani and Lauren Myers. So today I'll tell you about DICON. DICON is pronounced like the radish, and what it is an optimization system, where you specify a simulator and an objective which you'd like to optimize. You also specify a strategy space over which you would like to do the optimization, and what DICON returns to you after it runs is an optimized strategy. And in particular, DICON's optimization is specialized to epidemic disease control in the following ways. First, it expects a stochastic simulator, since often disease simulators are stochastic. It uses recent optimization algorithms. It's also parallelizable and scalable, so it can run on hundreds of machines on a supercomputer and on your laptop. And this gives you the ability to test many scenarios quickly. And in particular, DICON is more than just an optimization system. It's a community of packages. We've designed it to be modular and extensible. So for example, optimization algorithms are modules. You can swap them out to see how different algorithms perform. Basic epidemic simulators are also modules, so you can switch out the simulator that you use or even plug in your own. And also DICON comes along with separate visualization packages to help you visualize the outputs of your simulator. So here's a brief overview of the rest of the talk. I'm going to start by defining the optimization problem that DICON addresses. I'll go over some of DICON's features and also some of the community packages that come along with DICON. I'll focus on some of the differences from existing systems at the end and conclude with current and future work plans. So let's first define the optimization problem addressed by DICON. Suppose that we have a large strategy space of possible intervention strategies we'd like to use to try to stop a disease or alter a disease's course. So for example, A1 would be the strategy we take in the first time period, A2 would be the strategy in the second time period, and so forth up until a time horizon D. In addition to this big strategy space, we have a simulator that takes in a strategy and evaluates the strategy. And of course the simulator is random because it's simulating disease, and so what the simulator really does is return a particular draw from a random variable. And what we'd like to do is find the strategy that maximizes the expectation of the simulator. So just to put this into context, you can think of the simulator returning something like the number of people that didn't get sick. So we'd like to maximize that over all possible intervention strategies. And what DICON does is it automates the search for a good strategy in this kind of problem setup. So here's the basic DICON organization. What you see in red are parts provided by the system, for example an optimization manager and optimization algorithms. And in blue you see what should be provided by the user, which is basically a disease simulator, a policy space, some data parameterization to parameterize your simulator. So here are some of DICON's features. First, it has swappable, extensible optimization algorithms. It has built-in recent bandit search tree algorithms, for example UCT. It also has built-in exhaustive search, and we've designed it so that it's easy to interface to add new algorithms. So for example, you could add generic search algorithms like simulated annealing or your customized search algorithm. Second, DICON features automatic parallelization. This allows your program to run, for example, 1,000 instances of your simulator on 250 4-core machines. And what this does is it allows computations that would have taken maybe 3 years on your desktop to take a little over a day on a supercomputer. So the system really scales both from an individual machine on a laptop to many, many instances on a supercomputer. And to do this, it uses standard MPI interprocess communication. DICON also allows you to automatically parallelize your optimization. For example, you can run multiple optimizations at once. It has automatic assignment of multiple simulators to a single optimization if the optimization can use it. It also automatically queues jobs if there's many, many simulations you'd like to run but you don't have enough processors to run them all right now. Third, DICON features language-independent specification of the simulator and your strategy space. So you really get to define your simulator and your strategy space using your favorite language. For example, you could use Python, C++, Java, or really any other language like Scheme or Haskell. And the way that we do this is we use Google protocol buffers to do inter-process communications. For the techies in the audience, you can think of Google protocol buffers as just an efficient form of XML. Fourth, DICON features a very simple interface. Everything you write, for example, is single-threaded, and the system automatically parallelizes it for you. All you do is write one function to run the simulator, a simulate function that takes in a sequence of actions, and one function to define the policy space. This function is called next action, and what you do is you pass in a sequence of action, and it returns the next options of the action that could be taken. Fifth, DICON features versatile job specification. For example, you can run many optimizations with a single command. So oftentimes when you're doing these epidemic simulations, you want to try out many parameter values. And DICON lets you automate this very easily. You specify all of the values you'd like to try ahead of time, and it can parallelize those runs across the supercomputer. And of course, you can use this to select different policy spaces over which to do optimization, or even different algorithms which to use to do your optimization. Finally, DICON features logging and checkpointing. And this is really useful because often on a supercomputer, your runtime is limited to something like 48 hours. So DICON lets you continue interrupted optimizations. It also lets you monitor the ongoing process of optimizations, and it lets you log arbitrary data from your simulator based on your specifications. So zooming out a little bit from the system and looking at some of the community packages that would come along with it. First thing that we're planning on providing is a city network simulator, where you're allowed to stick in an arbitrary compartmental model inside a particular city. And then the network does travel between cities. This is also modular, so you can change the parameterization of the network. You can have different nodes and travelers between nodes. You can also switch out the simulator that's happening inside the city. We'd also like to add other epidemic simulators. For example, a demographic compartmental model where we split out demographic groups like pregnant women, children, adults, and so forth. A network simulation-based model where each node is an individual. And of course, DICON has the ability to use any simulator that you write. So we would like to really stick your favorite model into a community package as well. In addition, DICON comes with some visualization tools that are separate from the simulations. And so these could be used to visualize your model. Let me show you how some of these work. So in this visualization, the circle sizes represent city population. So for example, larger circles represent cities with bigger populations. Now, as we run the simulation on the left-hand side, you can see SIR curves. And the simulation automatically highlights routes of transmissions, both cities where the disease is happening right now, and links that are transmitting the disease from one city to another. And you can see that the simulation also identifies SI and R values using these pie charts inside of each city. You can zoom into a particular region of the geographic network if you'd like to focus on that region instead of the whole network. You can also change the way that a projection is done. So for example, from a flat projection to this round projection. In addition, the visualization comes with what's called a picking mode, where you can mouse over a particular city and then see city-specific statistics. For example, the SIR curves for this city in specific instead of the generic aggregate SIR curve that you see on the bottom right. It also gives you specific numbers for the infected and recovered in that city at that time. Because the visualization is separate from the simulation, this doesn't really tie you down to using a particular model. So you can stick in your favorite model and use the same visualization tool. And DICON is different from other optimization systems, specifically because it's specialized for epidemic disease control. And it expects random variable evaluations of the objective function. It's written so that it's highly parallelized for large optimizations running on a supercomputer. and it has a community of supporting packages to help you with your epidemic optimization needs. It's also different from other epidemic software packages because it specializes in optimization of control strategies. It's also language independent, which lets you use your simulator that you have right now without rewriting it. And also because of that, you can do optimizations using models from other packages. We already have used DiCon in some preliminary work. For example, we've used it to do antiviral distribution schedules of the US national stockpile. We've also used it to automatically identify key cities in the spread of an epidemic. Currently, we're working on extending the documentation and examples for DiCon. We've already started a community website to share and download the DiCon and the DiCon community packages. We're working on simulator bundles, some of the ones I already told you about in this talk. And we're also going to include more visualization and other alternate optimization algorithms in the future. Thank you very much, and consider using DiCon for your next optimization epidemic project. Thank you for listening.